Dejan, how are you? Good to see you.
Good to see you too.
Dejan, we're very excited to talk to you about your wafer scale designs that you're working on with your grad students right now. And I wondered if you could share your challenges with the current design flows and methodologies and what you would like to see change to enable more productive wafer scale design.
Yes, absolutely. So wafer scale is really scaling up the design complexity from reticle, which is a couple hundred millimeters square, let's say 400 to 800 in that range, square millimeters, to something that's 40,000 square millimeters. So that's the scale of complexity that we're talking about. If you take the whole 300 millimeter wafer and take a square piece out of it, that's about 200 by 200 millimeters. And at that level, we want to tile up various chiplets that can be homogeneous or heterogeneous, place them very close to each other, like macros that are about 100 micron apart, and stitch them up with a routing in between. Also provide utility signals for power and clock, and make sure that everything checks out at the top level. When you have such a large system, routing becomes very challenging. So if you have, let's say, 20 square millimeter chips, for 20 square millimeter chips, we have about 2,000 of those chiplets. Even if you make them uniform, you need to be able to make routing consistent, and just putting a router to do that seems to be very challenging. So even if it's straight lines, there is a lot of them. And we have been trying to circumvent issues by writing our own tools to make those routes feasible. And then after that, we would need to do LVS, because you take these chiplets face down to make sure that you account for all of the mirror effects and orientation of the pins and the pin maps, and be able to do all of it at the wafer scale with the design kits from the silicon interconnect fabric. So you have multiplicity of these macros that can be even in different technologies. And then what's common is the silicon interconnect fabric, which gives you a couple more layers of signal routing that you need to connect up all those pins and be able to do that within the DRC rules of the silicon interconnect technology, and do the LVS in the end.
Yes, Dejan, I can see where that's going to cause some problems with the current methodologies and the current tool sets. So we look forward to working with you on that. One of the things I wanted to ask you is about the wafer itself, and you're using both CMOS and 3.5 materials on the same substrate and the same interposer?
That's a possibility. We can support heterogeneous integration, although for now we use CMOS technology only, and chiplets that are built in possibly different technology nodes. We can mix and match chiplets built in different technologies, as long as they have the same communication protocol for signaling and power.
Are you using method of moments analysis or full 3D EM analysis?
We use separate thermal analysis tools. We use 3D and E&M analysis for other applications that I mentioned earlier when we talk about building electronics for biomedical implants. The heterogeneity of domains is different because then that's where we bring a lot of materials considerations for biocompatibility. When we build interfaces with the electrode arrays, they need to be electrically compatible. They also need to be mechanically robust for handling, and also need to be chemically adequate for biocompatibility issues. So there is quite a number of domains that need to be jointly considered in that regard. And also similarly, when we build antennas, RF antennas for communication and power charging, the power levels are very different than the wafer scale system, but it also brings us a lot of issues that we need to understand from the specific absorption. Then we really need to do like a 3D solvers, wave solvers for electromagnetic properties of those antennas and propagation through the body. And I mentioned already the electrodes and materials associated with that. So that's also something that we do, kind of E&M simulations for antenna and RF pieces that we then piece together with the electronics modules. And at that level, I think that's probably a good system to experiment with, because the level of complexity is relatively small compared to the wafer scale, but the amount of heterogeneity is perhaps even greater. That involves many different domains of analysis and different kinds of tools that you start to think this is no longer EDA problem. This is more like
it's a system problem.
System problem, and many kind of computational engines that you need to put in there to be able to wrap your hands around the whole system.
Thank you, Dejan. Thank you for the discussion.
Thank you, Doug. My pleasure.